Hello, and welcome back to Introduction to Genetics and Evolution. In the previous videos, we've been looking at concepts related to the amount of genetic variation in populations relative to the amount of total phenotypic variation. Now, as I mentioned before, this genetic variation is that subset of the variation which can be used by natural selection. So let's talk about natural selection for a minute and apply this to a couple of other areas. And very soon you'll see we'll be transitioning into population genetics. Well, natural selection is both non-controversial and, as I mentioned before, it is a mathematical inevitability. It's a mathematical inevitability if three simple conditions are met. First, you have phenotypic variation. We talked about phenotypic variation just recently in the context of quantitative genetics, and that would be that VP is not zero, that basically everybody doesn't look exactly the same in every way. Some of that phenotypic variation you see is actually inherited or genetic. In that regard, we're saying that the heritability is not zero. So you see, I'm introducing the same terms we did before, but now with some quantitative genetics behind them. And last but not least, this variation that is inherited, must affect either survival or reproduction. Now, let's walk through this very simple cartoon which illustrates this point nicely. So here we have several peppers that vary in their mildness or hotness. There's some that are mild, some that are hot. So there is this variation. This variation is inherited. The mild peppers give birth to other mild peppers. The hot ones breed other hot ones. Here's an interesting point I haven't emphasized so far, but this is relevant for today's lecture. More individuals are born than will survive to reproduce. Our capacity for population growth tends to be very high. We'll come back to this in just a moment. And related to this, some variants that survive or reproduce at higher rates than others. In this case, we can see that the milder peppers don't survive as well as the hot peppers because the mild ones get eaten up by things like mice or humans who like mild peppers. The outcome of this is that the population changes over time. That over time, as this is iterated over and over again, more of the surviving peppers will be hot because you've eliminated them, not only the mild peppers themselves, but even that genetic contribution within the population that made the peppers mild. Now, if we go back in time, that original concept of natural selection was very intrinsically tied to that of population growth. And Darwin's ideas were very much influenced by Malthus, who was an economist. Malthus had pointed out that populations are actually kept from growing by limited food and resources. Because again, our capacity to breed is very, very great. And if you provide more and more food to particular species, you'll tend to see that they will reproduce at a higher rate than is needed just to recreate the number of individuals present. That basically the population will grow if it is able to grow, almost always. Now, Darwin pointed out that this limitation produces struggle when some subset that are better able to survive or reproduce will tend to spread. But let's look at this concept of population growth. And why is it that natural populations grow so much? Why do we see this potential for great growth? Well, the capacity for growth is huge in most species out there. Now imagine, to maintain a constant population, assuming population was sexual, assuming you need a pair of organisms to breed, each pair would only need to produce 2 surviving offspring. Now, if conditions are favorable, how many offspring can most individuals produce? Well, look at some plants, for example. Let's say you're looking at seeds or pollen. Here's a picture of a tulip stamen and all the pollen on it. Look at all those individual grains of pollen on there. How many possible offspring could that tulip have? Definitely a lot more than 2. Think about insect larvae. You know, if you let an insect breed, how many offspring can it have? Think about things like cane toad eggs. Cane toads, as I mentioned a long time ago, are an invasive species in Australia and also in Hawaii, and they can have, hundreds, thousands, of offspring just from one breeding pair. And it's even true for humans, that if humans were allowed to in some way, we could potentially, one couple could produce many, many, many kids, easily, 10, 20, something like that. Now, we like to model the rate of increase and see how it's actually happening. Well, populations can be modeled with what's referred to as a stable rate of increase. This is assuming that a steady fraction of the population, or the population increases by a steady proportion year after year. To model this, we need a couple of parameters. We need a birth rate, which can be modeled as, for example, number of births per 1,000 per year. We need a death rate, number of deaths per 1,000 individuals per year. And from this, we can come up with what's referred to as the intrinsic rate of increase of a population. That is very simply the birth rate, so the input, minus the death rate, which is basically the output from the population. So in the United States, as an example, the birth rate is about 14 per thousand. The death rate is about 6 per thousand. So that makes the intrinsic rate of increase about 0.008. In this case, this is not considering immigration. This is just looking naturally. What this means is the population will grow naturally by 0.8% per year. Now, if the birth rate is greater than the death rate, then the population grows. And conversely, if the birth rate is lower than the death rate, then the population will decline. Now, so let's look at the effect on population size. Now, we'll go through a little bit of math here just to work this out. I hope you don't mind. So let's say that n is the population size and t is time in years. Now, we can identify a standard rate of population growth as dn over dt, or change in population size over change in time. And that would be equal to that rate of increase times the population size. Now, if we want to get an algebraic solution, if we assume that this was a constant process, we can approximate this as n sub t, so the population size at time t, is equal to n sub 0, which is that starting population size, times e. E is the algebraic number you often see. I think it's approximately 2.71. E to the power rt. R being that intrinsic rate of increase, and t being time. So time may be measured in years. So what is the population doubling time? How long does it take for a population to double its number of individuals, right? Obviously, that's going to be related to R. It's going to be related to the rate of increase. That if R is very large, the doubling time will be very short. If R is very, very small, then the doubling time will be very long. But let's put some actual numbers on this just so you can see. Here's the number. This is the formula I showed you before. N sub t equals n sub 0 times e to the rt. So what we want to do is we want to solve for the doubling time. So let's say that our n sub t is actually 2n sub 0. And what we want to do then is solve for t. So n sub t is equal to 2n 0. So we can substitute that in the equation. 2n sub 0 equals n sub 0 e to the rt. Okay. We divide both sides by n sub 0. That's very easy. 2 equals e to the rt. Well, this is very simple now. We just take the natural log of both sides. Right? So we take the natural log, and we have natural log of 2 is equal to natural log of e to the rt. Well, natural log of 2 solves out to 0.693, and that's equal to rt. Now, I said what we wanted to do is we wanted to solve for the doubling time. So we want to solve for t. So we just divide both sides by r, and there we go. T is equal to 0.693 divided by r. Okay. Well, I have here the numbers for the U.S. So the approximate U.S. population at the time this was recorded is 310 million. R is equal to 0.006. So what would the doubling time then be for the United States, just given its intrinsic capacity? Well, in the case of the US, it would be 0.693 divided by 0.006, because that's your R, which is equal to 115 years. So that's the time it would take for the US population to get to 620 million. That's huge. Now, 115 years sounds like it's a very long time from now, but really, it's just a little bit over a human lifetime. Well, let's try another one. This is a problem I'd like you guys to try. Notice it doesn't really matter in this case what the actual population size is to get the doubling time. You don't actually need to know n sub 0. Solomon Islands. Here's some numbers I got from Wikipedia. The birth rate on Solomon Islands is about 35 per thousand. Death rate is about 5 per thousand. Population size today is 500,000, though you don't need to know that. How long would it take to get to a million? How many years would it take to get to a million? Well, I'll let you solve that problem here on the question online. Well, I hope that one wasn't too challenging. Very, very simple problem. What we want to do is we want to calculate R. R, as I mentioned before, is equal to the birth rate minus the death rate. So it would be 35 per thousand minus 5 per thousand, which in this case would come out to 0.03. So that's your R. So when we want to calculate the doubling time, say doubling time, in this case t would equal to R, or 0.693 divided by R, 0.03. Which in this case comes out to 23 years. That's really dramatically fast, isn't it? That's changing the population on these islands from 500,000 to a million. So you're doubling the population size in 23 years. Well, we've seen a lot of population growth throughout the world, and I'll show you some pictures from a recent article in Science. This shows This first figure shows historic and projected future population growth. So you notice that the world population was very low, and we start seeing here very, very recently, just in the last couple of hundred years, this dramatic increase in numbers of individuals. So we hit 1 billion in the year 1800, we hit 3 billion in 1960, 4 billion in 1974, 5 billion in 1987, 6 billion in 1999, 7 billion in 2011, and it's projected we'll hit 8 billion by around 2024. This divides it up by some countries, where you're looking at some of the developed countries, some less developed countries, Africa as a continent, China by itself, and India by itself. So this is projections up to 2050 in this case for world population growth. Now, interestingly, our rate of population growth has actually gone down. Now, we are still increasing. R is still positive, that the birth rate is still exceeding the death rate, but the amount with which it's exceeding it has actually gone down over the last couple of years. But it's still positive, and that's why we're continuing to see this very rapid increase. Now, this is something that several different countries have attempted to address. One example would be China. China, as many of you know, back in 1979 instituted the one-child policy. This shows you the population growth in China over time. And this shows you the age distribution as of 2009 within. Now, you may be thinking, like, well, why is this still going, right? Because we have the one-child policy instituted around 1979, 1980, yet we still see this increase. Interesting, if you look at this, the increase is actually closer to linear than it is to exponential. Like, it's not going up, it's not continuing to accelerate as you would expect. So this probably has actually had some effect on slowing population growth. But, again, the birth rate is continuing to exceed the death rate. So we're still seeing an increase in the population size in China, as in many other places in the world. Well, why is that? Well, again, we have two causes of population growth. There's high birth rate, and there's low death rate. So we can cut the birth rate, but we still see growth. And what that means is that the death rate is decreasing faster than the birth rate is decreasing. Now, that's not intrinsically a bad thing. Obviously, we like decreasing our death rate. We don't want to have people just die willy-nilly, of course. But this is a problem in terms of how many people are on the planet. Over the course of many countries and over the course of a lot of recent time, we've seen this declining mortality or declining death rate. And some of it is associated with things like the introduction of the use of soap, improved sanitation. Definitely things like antibiotics and other modern medicine have really increased life expectancies. I can show you how much, too. This is just showing the difference between 1950 and 2010. And look at this. In Latin America and the Caribbean, we have an increase in life expectancy from 51 years to 73 years. In Africa, from 38 to 55. North America, 68 to 78. And just over the course of the whole world there, we can now expect to live 20 years longer than we could before. And as a result of this, we're seeing this just increased life expectancy at birth. And this, again, divides it up by several countries. Now, again, intrinsically, it's not a bad thing that populations grow. However, there is some maximum number of individuals that can be sustained on the planet. We'll come back to this question in the next video. Thank you.